Yay!
Yay! All right, let's see how to deal with gravitational potential energy. Because a lot of times when you're dealing with problems in motion of spacecraft or in the solar system or whatever, what you're really interested in is energy. So if we can use energy equations, that's going to be a lot more convenient than dealing with like force equations, because we know energy is conserved, right? Sometimes this is an easier approach. So let's see how this works. The principle is that the gravitational potential energy is minus, that minus sign is crazy important, g times the product of the masses involved divided by their distance. That's it. And it's not r squared, right? It's r, because you have to integrate the force, and so you get the minus 1 over r. That minus sign is really, really important, and that's a common mistake that people make when they try to solve energy problems, is forgetting that minus sign. And then we'll talk about why that minus sign has to be there. Hopefully, in a couple of minutes here, it'll make a little bit more sense. Okay, let's take the example of launching something. Let's just call it the Earth. But anyway, launching something from the surface of a planet, let's say the Earth. And we're just going to launch it with some speed v. And what I want to know is, there's a critical point where at infinity, when it gets infinitely far away, it'll just come to a stop, right? That's sort of a critical point. Imagine launching it just a little bit slower than that. So it's sort of like throwing something up in the air. You throw it, but you're not throwing it fast enough to where it'll escape completely. It'll turn around and then come back down again. On the other hand, it's possible, you could imagine, that you could throw something so fast that the gravity of the Earth could never sort of turn it around, and it would just escape. It would escape the gravity of the Earth. In fact, we're going to call this the escape speed, that critical point where if you throw something fast enough or launch something fast enough, it can just get out to infinity exactly when it coasts to a stop. It's not quite realistic, right? But it's sort of a boundary between falling back again and then keeping going. All right, so we want to find out this critical point. What is v escape? How we're going to find the escape speed is using energy methods. So what we're going to do is calculate the initial energy and the final energy. Just like we did for any other energy problem. All right, the initial energy. So that's when we launch the thing from the surface, right? So the initial energy, okay, we're going to do EI equals EF, right, as usual. Now, the initial energy, that's just kinetic plus potential, right? So it's launched with some speed, 1/2 mv squared. And then the potential energy. Okay, here's where you got to be careful. When we were doing energy problems before, we said, oh, you're on the ground, that's potential energy 0, right? Now, that's not true anymore, because now we're going to set the 0 point of potential energy to be at infinity. So U equals 0 is at R growing to infinity, really, really, really far away. And it kind of makes sense when you think about it, because when does something have no gravitational energy? Well, when you're infinitely far away from something, it won't feel the gravity at all. So it kind of makes sense. So if the potential energy is 0, really, really, really far away, then when it's close in, we're going to call that negative, more and more negative, for, again, reasons that I'll talk about in just a second. Anyway, we have to add that potential energy, and it's got a negative sign. So I have to write that in, minus GMM over that R. How far are we away from the center of the Earth? What's the gravitational potential of the Earth? Well, we're R away from the center. R. There we go. That's the initial energy. Okay, now the final energy, when we just reach escape speed and we get to really, really, really far away, the boundary is that we said the escape speed is such that the velocity goes to 0 when you're infinitely far away. So the kinetic energy is going to be 0 because it just comes to a stop. And when you're infinitely far away, we said the potential energy is also 0. 0 plus 0. There we go. So it's 0. Don't even have to get the calculator out. Okay, so let's solve this, and then we'll just briefly talk about it a bit. Okay, well, the mass doesn't matter. Cancels out. And so what is this escape speed? V squared. Well, let's just go ahead, and this can be easy enough to just solve it. So V, the escape speed, is just going to be square root of 2 gm over r. There we go. That's the escape speed. That's how fast you have to go to completely escape the gravity of some massive body. It looks a little familiar, right? Our orbital speed we got a couple of videos ago was just the square root of gm over r. So this is, to escape, you have to go square root of 2 faster. It makes sense that, you know, if you're in orbit around something, you're still sort of captured by the gravity. And it makes sense if you want to escape the gravity, you have to be going faster than that. It's interesting it's a square root of 2 faster than that. But anyway, here we go. So this is the escape speed. If you want to plug in the numbers for the Earth, for Earth, the escape is, what's that going to be? 6.67 times 10 to the minus 11. Let's just get it roughly. The mass of the Earth is 6 times 10 to the 24th. The radius of the Earth is 6.4 times 10 to the 6 meters. Look, we'll do the same trick, and I can do anything I want if I put that little squiggle up there. So let's just, those are, yeah, it's close, right? Let's just cross. I'm crossing it off. Let's cross that off. So we get something like, what is that? 12 times 10 to the 13 over 6, 7. So this is going to be something like 12 times 10 to the 7th. That's no good. Nobody likes that. But I can make that into something a little bit nicer if I just move a power of 10 over. Right? This is going to be the same thing as 120 times 10 to the 6th. Ooh, that's going to be really easy. Because what's the square root of 10 to the 6th? 10 to the 3rd. What's the square root of 120? Well, it's like 11. It's pretty close to 11. So the escape for the Earth is something like 11,000 meters per second, 11 kilometers per second. So that's how fast you're going to have to throw something, a baseball or whatever. What is it, 23,000 miles an hour. And it'll never come back down again. It'll just keep on going forever. If you put the sun's mass in there, so how fast, I mean, if you escape the Earth, that's cool, but can you escape the solar system? No. So if you start off where the Earth is, V for the sun, if you start where the Earth is, make that your R and put in the sun's mass, that would be, oops, that would be 2 g mass of the sun divided by our distance from the sun. You put those in and you're going to get something like 42 kilometers per second, a lot faster. So escaping the Earth is one thing, but to escape the sun, starting from the position of the Earth, you're going to have to go 4 times faster. And remember what that means, 4 times faster. That means you're going to need 16 times more energy, 16 times more fuel. So escaping the sun is actually a pretty difficult thing to do. Escaping the solar system is a difficult thing to do. All right. Let's talk about that just for a second. Let's go back. Notice what was happening. When you start off in this position, the gravitational potential was negative. And then what happens is you have to add energy to yourself, right? You have to add energy in the form of kinetic energy. You have to fire your rockets or whatever. You have to add energy just to get that energy up to 0 way out here where you're not bound anymore. Negative potentials like that are really hallmarks of bound systems because you're bound by the gravity, right? You have to add energy to get something up to 0 energy where it can escape. So that's why the potential gravitational potential energy has to be negative, because you have to add energy to it to get to 0. And after 0, you know, then for positive energies, then you're unbound. So the reason that we put that negative sign there, and the reason why it's so important, is because it indicates a bound system. You have to add energy to it to get unbound. Oh, one other little thing is, so it's 11 kilometers per second to escape the Earth. It's 42 kilometers per second to escape the sun, starting off at the Earth's position. I mean, how big can that number get? Well, you might know that the fastest speed that you might be able to think of is the speed of light, c, right? So what if the escape speed were the speed of light? If v escape equals c, 3 times 10 to the 8th, well, that would mean that you'd have to go the speed of light to escape this thing, which is impossible, for reasons that you'll find out in a subsequent course, hopefully. So if nothing can escape something, not even light, we would call this a black hole. And look, from that speed from the expression for the escape speed, if I know the v, and let's say it's something with the mass of the sun, I can calculate the r. How big would this thing have to be in order that its escape speed is the speed of light, in order to make it a black hole, for example? So for the sun, got to be able to spell solar. A solar mass black hole would have a size of, well, we can just solve for r, right? So r, in this case, is going to be 2gm over c squared, where that's the mass of the sun. And if you plug those numbers in, you get something actually really, really tiny, which is something like a radius of 3 kilometers. So if you squashed all the mass of the sun down to something that is just 3 kilometers in radius, so what is that? That's only like 3 miles across, something like that. It would have a surface gravity so intense that nothing could escape, not even light, and so we would call that a black hole. This sort of a size is called the Schwarzschild radius. You can plug in the Earth's numbers. What if you squash the mass of the Earth down to something really tiny? When does it become a black hole? That's when the Earth is squashed down to something like the size of a golf ball, maybe a centimeter in radius, something like that. So this is an extreme situation, but these bizarre objects apparently actually exist, which is the crazy thing. But we can gain some insight about them from even these simple energy equations, which is cool.